Chapter 7 Weight and Balance Introduction. This chapter is intended to help the instructor to teach the student the basics of helicopter weight and balance and how to compute the weight and balance forms. Definitions are abbreviated slightly, as the instructor's experience is recognized when working with the weight and balance form and records. It is not intended to instruct the student on the actual weighing of aircraft. The student must understand the reasons for weight and balance control. Listed in Figure 7.1 are some of the important topics of discussion. Discuss the list with the student. Refer the student to the Aircraft Weight and Balance Handbook, FAA-H-8083-4, as well as the Rotorcraft Flight Manual for that specific helicopter. Weight. The weight of a helicopter is critical during any and all flight maneuvers. This chapter primarily considers the weight of the loaded helicopter while at rest. Definitions discuss all the weight and balance terms with the student, which can be found in the Aircraft Weight and Balance Handbook, FAA-H-8083-4. The student should have an understanding of the terms in order to consistently and successfully monitor weight and balance and complete weight and balance forms. Never intentionally exceed the load limits for which a helicopter is certificated. Operating above the maximum weight could result in structural deformation or failure during flight if excessive load factors, strong wind gusts, or turbulence were encountered, as well as operating below a minimum crew weight could adversely affect the handling characteristics of the helicopter. Operations at or below the minimum weight of the helicopter can also affect the operational characteristics of the helicopter. Other factors to consider when computing weight and balance are high altitude, high temperature, and high humidity conditions, which result in a high density altitude. As density altitude increases, more power is required. Any adjustment to gross weight by varying fuel, payload, or both, affects the power required. For this reason, the maximum operational weight may be less than the maximum allowable weight. In-depth performance planning is critical when operating in these conditions. Most small helicopters have some type of seating limitations. Two examples are the Robinson R-22 and Robinson R-44. The R-22 has a 240-pound seat limit, includes any cargo below the seat. The R-44 has a 300-pound limit with a 50-pound cargo limit included within the 300 pounds. Therefore, if 50 pounds of cargo were placed under a seat, the passenger or pilot could weigh no more than 250 pounds. Also, the external load limit includes the weight of the load and the lifting slings and hardware. Determining empty weight. A helicopter's weight and balance records contain essential data, including a complete list of all installed optional equipment. Use these records to determine the weight and balance condition of the empty helicopter. Lead the student through a weight and balance problem, as well as pre-flight planning exercise before most flights. Once the student is proficient at weight and balance, then he or she should be allowed to reuse the previous planning information, provided that the conditions did not change. When a helicopter is delivered from the factory, the basic empty weight CG, and useful load are recorded on a weight and balance data sheet included in the Federal Aviation Administration, FAA-approved Rotorcraft Flight Manual, RFM. If equipment is removed, replaced, or additional equipment installed, these changes must be reflected in the weight and balance records. Major repairs or alterations must be recorded by a certificated mechanic. When the revised weight and moment are recorded on a new form, the old record is marked with the word superseded and dated with the effective date of the new record. Balance. Some helicopters may be properly loaded for takeoff, but near the end of a long flight with almost empty fuel tanks, the CG may have shifted enough for the helicopter to be out of balance laterally or longitudinally. Before making any long flight, the CG with the fuel available for landing must be checked to ensure it is within the allowable range. It is essential to load the aircraft within the allowable CG range specified in the RFM's weight and balance limitations. Center of gravity CG. The CG is defined as the theoretical point where all of the aircraft's weight is considered to be concentrated. Improper balance of a helicopter's load can result in serious control problems. The allowable range in which the CG may fall is called the CG range. The exact CG location and range are specified in the RFM for each helicopter. In addition to making a helicopter difficult to control, an out-of-balance loading condition also decreases maneuverability since cyclic control is less effective in the direction opposite to the CG location. Changing the CG changes the angle at which the aircraft hangs from the rotor. When the CG is directly under the rotor mast, the helicopter hangs horizontally. If the CG is too far forward of the mast, the helicopter hangs with its nose tilted down. If the CG is too far aft of the mast, the nose tilts up. Figure 7.2. Discuss with the student some of the reactions of the helicopter and problems associated with a forward CG and an aft CG. CG forward. A forward limit. Forward CG may occur when a heavy pilot and passenger take off without baggage or proper ballast located aft of the rotor mast. This situation becomes worse if the fuel tanks are located aft of the rotor mast because as fuel burns the CG continues to shift forward. Teach the student to assess the helicopter control response prior to each flight. Have the student get the helicopter light on the skid/gear and ensure helicopter is free of surface obstructions or attachments and will ascend to a hover in a nearly level attitude. Ensure that there is enough cyclic control to continue. Once at a low hover, ensure the helicopter remains nearly level. Point out to the student what a normal hover attitude looks like, and that if things do not feel or look right, then to lower the collective slowly and land the helicopter. Attempt to determine why the helicopter is responding in such a way. Adjustment or reduction of load may be necessary. Do not continue flight in this condition. Decelerating the helicopter in this condition may be very difficult or impossible as well. In the event of engine failure and the resulting auto-rotation, there may not be enough cyclic control to flare properly for the landing. CG aft of aft limit exceeding FCG may occur when a lightweight pilot takes off solo with a full load of fuel located aft of the rotor mast. A lightweight pilot takes off with maximum baggage allowed in a baggage compartment located aft of the rotor mast. A lightweight pilot takes off with a combination of baggage and substantial fuel, both of which are aft of the rotor mast. Easily recognized when coming to a hover, the helicopter has a tail-low attitude, and needs excessive forward displacement of cyclic control to maintain a hover in a no-wind condition. If there is a wind, even greater forward cyclic is needed. Note, one technique used in smaller helicopters is to show the student what a tail-low, nose-high, attitude looks like. To do this, seat the student, pilot's seat, in a parked helicopter, engine off. Pull the tail boom down or lift the front skids until the tail stinger or guard touches ground. Tell the student to commit this helicopter position to memory and never allow the helicopter to achieve this attitude while in flight. Gusty or rough air could accelerate the helicopter to a speed faster than that produced with full forward cyclic control. In this case, dissymmetry of lift and blade flapping could cause the rotor disc to tilt aft. With full forward cyclic control already applied, a pilot might not be able to lower the rotor disc, resulting in possible loss of control or rotor blades striking the tail boom. Lateral balance. Discuss with the student the problems associated with lateral balances. With small helicopters, it is generally unnecessary to determine the lateral CG for normal flight instruction and passenger flights. The cabins are relatively narrow and most optional equipment is located near the center line. If there is an unusual situation that could affect the lateral CG, such as a heavy pilot and a full load of fuel on one side of the helicopter, its position should be checked against the CG envelope. Certain types of helicopters require a pilot to verify the lateral balance often, such as external hoist operations, hoist located on the side of the helicopter. Helicopter engineers determine the amount of cyclic control that is available. They establish both the longitudinal and lateral CG envelopes. This allows the pilot to load the helicopter and still have sufficient cyclic control for all flight conditions. Operating the helicopter outside these limits is inadvisable and control of the helicopter may not be possible in some conditions. Ballast. Ballast is some form of weight placed in a specific location in an aircraft intended to maintain the CG within limits by compensating for unfavorable weight and balance conditions, thereby ensuring correct control margins. Two types are permanent ballast and temporary ballast. 1. Permanent ballast. The removal or addition of equipment to the helicopter has an effect on aircraft weight and balance. It may be necessary to install ballast weights to maintain the CG position within the CG limits. 2. Temporary ballast. Such weights that may be necessary to compensate for missing crew members or equipment in order to maintain CG position. The amount and location of temporary ballast required to maintain safe flight is determined by the pilot or the airframe and power plant, A&P mechanics. Ensure that any ballast is properly secured or strapped down to prevent movement. When ballast moves, it compounds the CG problem instead of relieving it. Weight and balance calculations. To determine whether a helicopter is properly loaded, ask the following questions. 1. Is the gross weight less than or equal to the maximum allowable gross weight? Answer. Add the weights of the items comprising the useful load to the basic empty weight of the helicopter, pilot, passengers, fuel, oil, if applicable, cargo, and baggage. 2. Is the CG within the allowable CG range, and will it stay within the allowable range throughout the duration of flight including all loading configurations that may be encountered? Answer. Use CG or moment information from loading charts tables, or graphs in the RFM. Then using one of the methods described below, calculate the loaded moment and/or loaded CG and verify that it falls within the allowable CG range shown in the RFM. Note, discuss with the student which direction the CG shifts as fuel is burned. On some helicopters, the fuel tanks are behind the CG, causing it to shift forward as fuel is used. Under some flight conditions, the balance may shift enough that there is not sufficient cyclic authority to flare for landing. For these helicopters, the loaded CG should be computed for both takeoff and landing weights. Use CG or moment information from loading chart tables, or graphs in the Rotorcraft Flight Manual, RFM. Calculate the loaded moment and/or loaded CG and verify that it falls within the allowable CG range shown in the RFM. It is important to note that any weight and balance computation is only as accurate as the information provided. Therefore, determine passenger weight and add a few pounds to account for the additional weight of clothing, especially during the winter months. The baggage weight should be weighed on a scale, if practical. If a scale is not available, compute personal loading values according to each individual estimate. Weight versus aircraft performance. Overloading an aircraft may cause structural failure or result in reduced engine and airframe life. An increase in gross weight has the following effects on aircraft performance. A. Increases takeoff distance. B. Reduces hover performance. C. Reduces rate of climb. D. Reduces cruising speed. E. Reduces maneuverability. F. Reduces ceiling. G. Reduces range. H. Increases landing distances. Note, ensure that the student understands the importance of not overloading the helicopter, operating at maximum weights, and also understands how the helicopter's weight versus performance is also affected. Accurate performance planning based on current and forecast environmental conditions is critical in determining the helicopter's actual maximum operational weight for any given set of conditions. Figure 7.3 indicates the standard weights for specific operating fluids. Reference datum. Figure 7.4 indicates some of the different locations of the horizontal reference datum. Balance is determined by the location of the CG, which is usually described as a given number of inches from the reference datum. The horizontal reference datum is an imaginary vertical plane or point arbitrarily fixed somewhere along the longitudinal axis of the helicopter from which all horizontal distances are measured for weight and balance purposes. There is no fixed rule for its location. It may be located at the rotor mast, the nose of the helicopter, or even at a point in space ahead of the helicopter. The lateral reference datum is usually located at the center of the helicopter. The location of the reference datum is established by the manufacturer and is defined in the RFM. Figure 7.5, the lateral CG is determined in the same way as the longitudinal CG, except the distances between the scales and butt line 0, BL0, are used as the arms. Arms to the right of BL0 are positive and those to the left are negative. The BL0, sometimes referred to as the buttock, is aligned through the symmetrical center of an aircraft from nose to tail. It serves as the datum for measuring the arms used to find the lateral CG. Lateral moments that cause the aircraft to rotate clockwise are positive plus, and those that cause it to rotate counterclockwise are negative. Arm, station, the horizontal distance from the datum to any component of the helicopter or to any object located on the helicopter is called the arm or station. Moment. If the weight of an object is multiplied by its arm, the result is known as its moment. Think of a moment as a force that results from an object's weight acting at a distance. Moment is also referred to as the tendency of an object to rotate or pivot about a point. The farther an object is from a pivotal point, the greater its force. Weight and balance methods. Discuss with the student the two different methods of obtaining the weight and balance of the helicopter, computational and loading chart. Computational method. The first method is the computational method, which uses simple mathematics to solve weight and balance problems. 1. Ascertain the total weight and total moment of the helicopter and ensure it does not exceed the maximum allowable weight under existing or forecast conditions. In this case, the total weight of the helicopter is under the maximum gross weight of 3,200 pounds. Tip: the empty weight CG can be considered the arm of the empty helicopter. Use care in recording the weight of each passenger and baggage. Recording each weight and its proper location is extremely important for the accurate calculation of a CG. 2. Now, divide the total moment by the total weight. This gives the CG of the loaded helicopter. The bottom of the chart in Figure 7.6 lists the CG range for this particular helicopter. Take the CG figure and compare it to the allowable limits of 106.0 inches to 114.2 inches. The CG's location of 109.9 inches is within the acceptable range. Note, if the CG falls outside the acceptable limits, adjust the loading of the helicopter. If adjustments need to be made to the loading, refer the student to the Aircraft Weight and Balance Handbook, FAA-H-8083-4. Loading chart method. The second method is the loading chart method. 3 sample problems are given for this method. Take time to ensure the student fully understands the weight and balance concept and computations. Figure 7.7 is an example of a loading chart. To use this chart, a pilot must 1. Subtotal the empty weight, pilot, and passengers. This is the weight at which to enter the chart on the left. 2. The next step is to follow the upsloping lines for baggage and then for fuel to arrive at a final weight and CG. Note, any value on or inside the envelope is within the range. Sample problem 1. The student may not understand how or why the numbers are entered on the chart. Explain the numbers to the student. Most manufacturers provide samples with their charts. Figuring the charts out is a matter of inputting your own numbers. The loading chart used in sample problems 1 and 2 is designed to calculate the loaded CG graphically and show whether it is within limits, all on a single chart. Determine if the gross weight and CG are within allowable limits under the following loading conditions for a helicopter based on the loading chart in Figure 7.7. To use the loading chart for the helicopter in this example, add up the items in a certain order. The maximum allowable gross weight is 1,600 pounds. Note, in Figure 7.7, the helicopter weights are located on the left side of the chart and the CG limits are located on the top of the chart. Item weight, pound, basic empty weight 1040, pilot 135, passenger 200, subtotal 1375, point A, 1. Follow the green arrows in Figure 7.7. Enter the graph on the left side at 1,375 pounds, the subtotal of the empty weight plus the pilot and passenger weights. Move right to point A, baggage compartment load 25 pounds, subtotal 1,400 pounds, point B, 2. Move up and to the right, parallel to the baggage compartment loading lines to 1,400 pounds, point B. Fuel load, 30 gallons 180 pounds, total weight 1,580 pounds, point C, 3. Continue up and to the right, this time parallel to the fuel loading lines, to the total weight of 1,580 pounds, point C. Point C is within allowable weight and CG limits. Sample problem 2. Assume that the pilot in sample problem 1 discharges the passenger after using only 20 pounds of fuel. Item weight, pound, basic empty weight 1,040, 135, pilot 1,175, point D, subtotal 1. Follow the purple arrows in Figure 7.7, starting at 1,175 pounds on the left side of the graph, then to point D, baggage compartment load 25 pounds, subtotal 1,200 pounds, point E, 2. Continue to point E, fuel load 160 pounds, total weight 1,360 pounds, point F, 3. Continue to point F. Note the total weight of the helicopter is well below the maximum allowable gross weight, however, point F falls outside the aft allowable CG limit. As standard practice, compute the weight and balance with zero fuel to verify that a helicopter remains within the acceptable limits as fuel is used. It is imperative that weight and CG be within allowable limits for all phases of the flight or successive flights. Weight and CG change as loading configurations change, therefore more than one weight and balance calculation needs to be accomplished. Initial calculations are based upon a fully loaded aircraft for the first takeoff. Subsequent calculations address loading configuration changes, such as passenger drop-off, fuel consumption and refueling. Addressing calculations for all projected loading configurations ensures that weight and CG remain within limits during all phases of the flight. Discuss with the student some options he or she could use in order to fix the out of CG condition. Sample problem 3. Calculate moments for each station. Weight, pound, moment item basic empty 1,102, pilot and front passenger 340, fuel 211, 0 baggage 1,653, total 10.8, 28.3, 22.90, 162.0. Use chart in Figure 7.8. 1. Record the basic empty weight and moment. 2. Record the weights of the pilot, passengers, fuel, and baggage on a weight and balance worksheet. 3. Determine the total weight of the helicopter. 4. Determine if the helicopter weight is within limits. Load limit on bottom of chart in Figure 7.9.5. Determine the moments for a pilot and passenger, 340 pounds, and fuel, 211 pounds. Figure 7.8.6. Using Figure 7.8, start at the bottom scale labeled load weight. Draw a line from 211 pounds up to the line labeled fuel, station 108.5. Draw a line to the left to intersect the moment scale and read the fuel moment, 22.9 thousand pound in. 7. Do the same for the pilot/passenger moment. Draw a line from a weight of 340 pounds up to the line labeled pilot and passenger, station 83.2. Go left and read the pilot/passenger moment, 28.3 thousand pound in. 8. After recording the basic empty weight and moment of the helicopter and the weight and moment for each item, total and record all weights and moments. 9. Plot the calculated takeoff weight and moment on the sample moment envelope graph. Based on a weight of 1,653 pounds and a moment/1,000 of 162 pounds in, the helicopter is within the prescribed CG limits. Note: reduction factors are often used to reduce the size of large numbers to manageable levels. In Figure 7.8, the scale on the loading graph gives moments in thousands of pound-inches. In most cases, when using this type of chart, a pilot need not be concerned with reduction factors because the CG/moment envelope chart normally uses the same reduction factor. Figure 7.9, Combination method. The combination method usually uses the computation method to determine the moments and CG. Then, these figures are plotted on a graph to determine if they intersect within the acceptable envelope. The example in Figure 7.10 illustrates that with a total weight of 2,399 pounds and a total moment of 225,022 pounds in, the CG is 93.8. Plotting this CG against the weight indicates that the helicopter is loaded within the longitudinal limits, point A. Calculating lateral CG. Some helicopter manufacturers require that pilots also determine the lateral CG limits. Lateral balance of an airplane is usually of little concern and is not normally calculated. But some helicopters, especially those equipped for hoist operations, are sensitive to the lateral position of the CG, and the Pilot's Operating Handbook, (POH), includes both longitudinal and lateral CG envelopes, as well as information on the maximum permissible hoist load. These calculations are similar to longitudinal calculations. However, since the lateral CG datum line is almost always defined as the center of the helicopter, a pilot is likely to encounter negative CGs and moments in the calculations. Negative values are located on the left side while positive stations are located on the right. When completing the steps below to calculate lateral CG, refer to Figure 7.11. 1. When computing moment for the pilot, 170 pounds is multiplied by the arm of 12.2 inches, resulting in a moment of 2,074 pounds in. As with any weight placed right of the aircraft centerline, the moment is expressed as a positive value. 2. The forward passenger sits left of the aircraft centerline. To compute this moment, multiply 250 pounds by minus 10.4 inches. The result is a moment of minus 2,600 pounds in. 3. Once the aircraft is completely loaded, the weights and moments are totaled and the CG is computed. Since more weight is located left of the aircraft centerline, the resulting total moment is minus 3,837 pounds in. To calculate CG, divide minus 3,837 pounds in by the total weight of 2,399 pounds. The result is minus 1.6 inches, or a CG that is 1.6 inches left of the aircraft centerline. Lateral CG is often plotted against the longitudinal CG. Figure 7.12, in this case, minus 1.6 is plotted against 93.8, which was the longitudinal CG determined in the previous problem. The intersection of the two lines falls well within the lateral CG envelope. Instructor tips: review all the terms associated with weight and balance with the student. Review the sample weight and balance problems with the student. Ensure that the student understands weight and balance must remain within limits after all loading, unloading, refueling, and fuel consumption. Ensure that the student understands current and forecast environmental conditions affect the performance of the aircraft, thereby affecting weight and loading limitations. Review and practice with the student the actual weight and balance forms for the helicopter to be flown. Ensure the student understands the charts by using weights and/or balances that may put the helicopter in an out of weight or out of balance condition. The more the student works the weight and balance figures, the more proficient the student will become at computing weight and balance. Figure 7.13, Chapter Summary. This chapter explained how to introduce weight and balance to the student, how to read the charts necessary for computing weight and balance of the helicopter, and definitions of common terms associated with weight and balance.